So, very good morning to all of you. The second day, first session. So, I hope all of you are doing very good. So, today we will not waste our too much time because I have a lot of things to say today. So, I will go directly to our presentation, whatever we are planning. I think my screen is visible to all of you, right? My screen visible to all of you, right? Yes, sir. Okay. Thank you, sir. Well, so just maybe last page in page 1 and as well as yesterday also, we were mostly focused on the device fabrication process and cleaning process. Today we will mostly focus on some devices, what can be done, whatever in page 1 as well as yesterday also. We several speakers, maybe Dr. Professor Gupta, Dr. Mondal, they already discussed several devices, sensor devices, flexible wearable devices, and a lot of things. Most of the things, those are all the devices are in the nano based, mostly nanotechnology based, or in the order of nanometer region. So today we will discuss about the some devices that whatever we are using in our daily life. That is maybe in your pen drive, in your mobile, in the computer, everywhere. So that is another device that is called memory devices. So this is my outline of the talk. I will tell about some introduction of the memory devices. I will tell some dynamic random access memory about something, flash memory devices, fetch memory devices, RAM devices, RAM devices, and application of the some RM devices. That is one of the best or very exciting work. That is, I will discuss or I will show some results on neuromorphic computing. So as I told, maybe previously we told maybe or you maybe know in your textbook. In your textbook, that memory are usually classified into two categories. That is, one is your volatile memory, another one is your non-volatile memory. So volatile memory that can be usually classified as a dynamic random access memory and static random access memory. These two are the volatile memory. And whereas non-volatile memory, it can be classified in the three categories usually: permanent charge storage, permanent polarity change, and conductivity change memory. Permanent charge storage, that is usually converted into one category, single category flash memory, whereas permanent polarity change, that is usually classified in the periodic RAM and MRAM. Read the word, that is permanent polarity change. Here change polarity change permanently, and here charge storage permanently. However, there is another change memory that is not permanent usually. We can say that the change can be random. We can say not in the same position. We can get the changes. That is conductivity change memory. That is RAM, resistive random access memory, fetch change memory, and conducting bridge random access memory, CBRAM, conducting bridge random access memory. All of the classified CBRAM and RAM, CBRAM and RAM, that is both are in the same category. Sometimes this is CBRAM also known as the type of RAM. Okay, or this is also known as the Memristor. Now I will go back to volatile memory once again. This is DRAM and SRAM, both are the dynamic volatile memory. However, SRAM little bit slower than the dynamic random access memory. That's why most of the computers till date are using dynamic random access memory for its fast switching, fast access, and very cheap and very inexpensive. So I can say my research area usually flash memory and RAM. I will mostly focus here in my research work. However, during my PhD, I have done most of the work on the flash memory, and at the end of the PhD, I have done RAM. And after PhD, I am still working on the RAM and its applications. So today, first I will tell you the dynamic random access memory. This is the DRAM architecture. I think those are having some electronics based background or some textbook background knowledge of physics. You know, this is the MOSFET or FET. So field of a transistor, this is source, drain, and gate. So this drain is connected with the over line, and in between the drain, in gate is connected with the over line, and here is a in drain. There is a one capacitor that is actually DRAM capacitor. Is usually metal insulator metal structure is connected here. So and we applied the voltage here. So once you apply the voltage, DRAM is switched or start working, and then you can get the some desirable memory property, or computer can be on, or some desirable properties for the dynamic random access memory. Keep in mind, DRAM or whatever MIM, this structure, cell capacitor, it's a capacitor, nothing but a capacitor. It can be worked. It can be worked if only after adding the transistor. Only capacitor cannot work. So there is a, I told you yesterday, this architecture must be one transistor and one resistor. So this is the schematic diagram, how it's working. This is pre-silicon MOSFET, and then here is the your some DRAM architecture is there. Well, now DRAM architecture, we will focus on the MIM part, that is DRAM part only. We will not focus on the total structure, what happened in the DRAM, and what even after connecting with the MOSFET, what happened. We are not focused on this. We will mostly work or mostly study only on DRAM part, only on memory part only. So this is architecture part, that is another research work, that is another part of the research. So we will not focus on there. So this is the general textbook knowledge. Maybe all of you know capacitance equal to dielectric constant into area by thickness. A is the area, T is the thickness. So to store property, to memory property means how much data we can store. That can be improved. Means suppose your RAM, your DRAM is your 64 MB megabyte memory you have. How much we usually ask your computer is how much memory? 128 megabyte, 1 gigabyte memory, or 4 gigabyte RAM is there. This RAM is nothing but a DRAM actually. So this DRAM is gigabyte. This is means how much capacitance is there. That is usually C is denoted by epsilon. Epsilon 0, epsilon, and A by T. Epsilon 0 is the, all of you know very well, free space permittivity. This is symbol is not there. And epsilon 0 is the dielectric constant of the material, whatever used in the this layer. This MIM means metal, insulator means dielectric layer, maybe oxide layer, maybe high-K layer. That is depend on the material, whatever we will study maybe a little bit more in the next slide. Okay, so this area is the dielectric area, means capacitance area, means oxide thickness. A is the oxide thickness. T is the A is the gate area, means how much device size area. T is the oxide thickness, and epsilon is the dielectric constant of the material. So to achieve the high capacitance, we must need to increase the area of the device. So if we increase the area of the device, then our main problem in issue is that your device sizes will be increases. So that is not desirable. We want our device should be smaller as possible. So that should not be, we cannot increase the device area or add too much. So in that case, another way we can increase our capacitance, that is we can decreasing by thickness of the material. Thickness of the dielectric material. If we decrease the thickness of the dielectric material, that is another trade-off will come. That is usually your effective oxide thickness, EOT, that will be decreases. So if the oxide thickness will decreases after some time, maybe 1 nanometer, 2 nanometer, you cannot achieve. That is definitely 1 nanometer you cannot achieve. Maybe for silicon dioxide you can go up to 10 nanometer or 12 nanometer. So after that, what happened? Direct tunneling happened between metal, top metal and bottom metal, or source or drain. So once top metal and bottom electrode, top electrode and bottom electrode both are connected, that time you cannot get the capacitance. Your leakage current will be hugely increased. So thing is that to increase the capacitance, if you increase the area, your device size is area. You cannot, you are bound there to decrease the area. So if you decrease the area, capacitance will be decreases. So another trade-off, that two much things, these two things, area and thickness, you cannot change. So that's why you have to change only here on. Now, if you were bound, suppose you are wanted to use only silicon dioxide. So silicon dioxide dielectric constant is fixed, you cannot change. So in that case, you have to use some high dielectric constant material, that is titanium pentoxide, hafnium oxide, or titanium dioxide. These are materials. So if you use these high dielectric materials, that time, if you, even though you can decreases the area as well as increases the thickness, that can be, you can achieve the high capacitance. So this is the main thing of the main motive of the how uses of the high K dielectric. Another thing also, the another way we can increase the capacitance, that is actually we can modify the area of the device, area of the electrode by hemispherical grain technology. That is, we will got cylindrical structure of the electrode. So that's why we can, by modulating, by engineering the electrode, we can achieve also the high capacitance. So these are the trades-offs. So high K dielectrics we have to use, and we have to also use the cylindrical and hemispherical grain technology, HSG technology for the train structures. Thickness of the films we have to limit it. We cannot achieve, we cannot go beyond this one. So that can be completed up to certain nanometer length. So for that, you have to tune the capacitors of the material. So this is the some TM structure of the some hemispherical grain architecture of the electrode of the maybe bottom electrode. So this is, you can see that there are some grains is there. This grain is made by the silicon, amorphous silicon grain is there. So this silicon grain, once you put the grain and the surface area is increases, that's why your capacitance is increases. So this is another some pictures are there. Definitely these are not our picture, that is they published in literature from the Samsung group, they published this one. For normal stack, normal electrode, they can go achieve up to 64 megabyte, megabyte. And wherever they use the some stack circuit, stack as well as hemispherical grain technology. These are the grains in the electrodes. They achieve little bit higher storage capacity. And once they engineer the structure in some different way, cylindrical, that can be achieved little bit less. Whereas if they use cylindrical with hemispherical grain, then can be achieved more capacity. So thing is that we can change the simple structure to complex structure to improve the capacitance, as well as we have to tune the dielectric constant of the material. That part we have shown in our maybe yesterday. So these are the another few structure of the lower hemispherical grain technology. This is some electrode, crystalline silicon is there, amorphous silicon is there, the lower electrode, and here crystalline silicon. These are the hemispherical grains are there. And this is the schematic structure of this one. So this is actually they fabricated using the just after annealing of the, after growing the seeding crystalline silicon layer, they anneal the sample and they go the crystalline silicon and as well as hemispherical grain structure. So by this way, lot of people they also achieve very good capacitance properties, very good by tuning the structure as well as the oxide thickness. So these are the some pictures. I'm not going to this one. So now another part is that now there is some comparison of the normal without hemispherical grain on silicon structure, and this is with hemispherical grain with silicon structure. You can see here about your capacitance about 12 microfarad, that 12 femtofarad per cell, and that is about we can achieve up to double almost over 2 times, usually 25 or more than 25 we can achieve by using the hemispherical grain structure. So same structure, by putting some nanoparticle hemispherical grain, they achieve this one. But trade-off is yet coming here. That is one problem is coming. That is, once you achieve the adding the hemispherical grain, your leakage current is increases. Keep in mind, leakage current for the memory devices any memory devices that may be volatile or non-volatile, that should be decreases. Because leakage current can, if current is increases, your power will be increases. We know that is not desirable. As well as your power, if power increases or current increases, your devices will be more heat up. So that is also not desirable. So these two things will be, you have to compromise. So by this way, you have to tune the device structure by using the different structure as well as different methods. Now, one other important thing is that these two measurements, such leakage current as well as the switching property, as well as the capacitance, or as well as all the IV property, electrical measurement, we cannot measure them in the normal electrical measurement. Or you have to use probe station. I know some of you already saw the probe station, but some of you not saw. So that's why I'm just showing a little bit small video to give the demonstration of the probe station. This is the schematic of the. This is the one probe station. Here is the. Yeah, this is the probe station. This is your chunk. This is your chunk. Chunk means where you can put your wafer or device here. This is your, I can say, little bit fast, then stop then. This is your microscope, because your device area, device sizes is very small. So for that, you have to probe connected with the microscope. You have to see the your device top electrode or dot or whatever we can say. That should be seen. You can have to observe by the microscope. And must be this area is not too much lighter, so that's why you put a light is there. And this is some movement you have to move. You cannot move the sample always. The sample is connected or fixed with the vacuum chunk. It's actually vacuum chunk. So when he has a small hole is there and small pump is there, so that is sample will be connected. Otherwise, when you are probing, your sample will be moved. So that's why it should be connected or fixed on the chunk. So then you have to move this chunk for the different devices. That can be XY direction, XYZ direction, P direction. Then you can move this one. And this whole the system will be shielded with the metallic box, so that you cannot electromagnetic radiation cannot affect your devices. Because electromagnetic radiation or light, whatever, or vibration, those things are affected too much onto devices. Usually, this system is put in the some vibrating vibrating table, so that it cannot be affected by the vibration also. So you can see a little bit how this is working. There are no videos, so don't worry about that. Yeah, this is the movement of your chunk or sample you can move. This is XY direction, and that is Y another direction, Y direction. You can move with this one, and here usually probes are there. That is not, maybe it's not shown in this picture. This is the fine alignment. You have to make the alignment using it should be vertical properly. So you have to do it yourself. You have to check it and do it. So this electrical measurement is very, very tricky and very, very important. So not only this one, you have to use some good measurement system that may be Kittley or Agilent. This is so we can go very high resolution current to femto ampere or very high resolution current. Sorry, capacitance. Okay, so these are the things. I'm not showing you too much thing. So that's why this leakage current is very, very important. So another thing we have done, or not I have done actually, this is also reported work. So that is what they had done. I told you a few minutes back for the metal insulator, and that can be metal insulator semiconductor structure also, or silicon structure also, MIS. If you use some highly doped silicon, that can be used at the bottom electrode also. So this insulator region, that means this is dielectric region, that is capacitance or dielectric constant of the material, that can be, you have to tune. So here they have carried the different dielectric constant, tantalum pentoxide and some hafnium oxide alumina asymmetric tunneling layer, maybe you can say. or bilayer they have used. Once they use that is for the same thickness for the tantalum pentaoxide, the effective oxide thickness is about 35 angstrom. Whereas 35 angstrom. Whereas for the hafnium oxide, alumina oxide, the effective oxide thickness for the physical thickness is for the both the cases same. I repeat once again, physical thickness of the tantalum pentoxide is both the and hafnium oxide, aluminum oxide thickness is same. However, effective oxide thickness that is decreases. So effective oxide thickness decreases means you can go for the lower device sizes. So, and whatever, another important thing that once the effective oxide thickness, your device properties also changes. You can see almost similar device properties. However, in the positive side, that little bit higher current for this one. So these things you have to compromise and you have to make the trial and error method which one coming the best. So there are a lot of oxides, lot of structures have been proposed for these things. So we are not going to this one. This is another structure they have used, that is for the tantalum pentoxide they have used, and they have used here alumina, tantalum pentoxide, alumina. So you have to play with the different oxide and you have to find. So here you can see that this capacity is about 9, whereas once you use this tri-layer structure about, but keep in mind both the cases are physical thickness is same. So your capacitance is hugely increases. Not only capacitance increases, your leakage currents also decreases. So as our desirable, that is also our desirable. Our desirable is the capacitance should be high, means we can store the more data. We can, our memory size should be, we are looking for the 4 GB, 8 GB, 64 GB. That is we are our aim. And definitely you don't want your computer should run in the high power. So that is you don't want. So that is your capacitance should be high and leakage current should be less. So that is our very good things, whatever they got. So this is the one on the simulated structure, how they fabricated this type of device. I'm just, yeah, okay. So this device structure, ultimately you are getting like that. This is your device structure. So for that, what usually they did, they make a actually simple lithographic process, maybe usually photolithographic process they use. They use the substrate and there they open the coated with the mold oxide that is usually used as a spacer also. And this is edge stopper, that is some chemical they have used, the stopping chemical edge stopper, and that they may open the some space. This portion is open by this is named by simple lithographic method on. Then on it they deposited the ruthenium layer. That ruthenium is the bottom electrode here. Once after deposition of ruthenium, they deposited some oxide layer, that is maybe tantalum oxide deposited on it. After tantalum dioxide, sorry, after ruthenium deposition, they make the lithography once again. They make opening space and they deposited again the tantalum oxide. Then again they deposited ruthenium oxide. They again ruthenium deposition. So they finally they go achieve this type of structure. You see, the violet one is your ruthenium, yellow one is your tantalum oxide, and this one is your ruthenium. So here from there you can get the bottom electrode. Then after that he removed all the. After that they removed all the things. This white portion as well as red portion they removed. So ultimately they achieve this type of structure. So ultimately they will achieve this type of structure. This structure is ruthenium, tantalum oxide, and ruthenium structures. So this is not very easy job to get such this type of structures, definitely. And then they measure the dish one and they measure the relative work function about all the physical parameters. And they do the some other processing, oxygen plasma etching, etc. They did for to achieve this type of thing. Then they measure the some electrical properties. Keep in mind, they anneal the sample at different temperatures. Some of you may not know what is annealing. Annealing means you have to, after fabrication of the device, you have to heat the sample in vacuum or your as per your desired ambient, maybe nitrogen or oxygen. That was your desirable, or vacuum, whatever, as per your desirable, as per your wish, whatever you want. So there at this ambient, you have to make it heat at different temperature. So that is called annealing for the semiconductor processes. So this is in degree centigrade. I don't know why this is not coming. So once you annealing the devices, we can see this is without annealing sample. That is effective oxide thickness about 23. Whereas if you anneal the sample at 700 degrees centigrade, the effective oxide thickness is decreases. So our goal should be low effective oxide thickness. And another thing will be happen. If you make the device having crystalline structure as well as amorphous structure, that can be done usually by your deposition process. As I told you before, ALD usually use for the crystalline structure, and sputtering you can use for the amorphous structure. After deposition also you can make it crystalline as well as amorphous by annealing process. Maybe oxygen annealing can give you, leads you amorphous, and vacuum annealing can lead you crystalline structure. That is depend on the device material, etc. So that is another what you can say. So if you get, and how do you know this is amorphous or crystalline? That for that you have to do some XRD, and from there you can know this portion, this structure is amorphous and this structure is crystalline. So amorphous means there is a lot of leaky spaces. So that is usually is very difficult to current conduction. Whereas crystalline means there is a very strong bond between the atoms, that can be, you can get the very current conduction very easily. So that's why you can get the very good current or very high leakage current, we can say, for the crystalline structure. But keep in mind, definitely once again, good current is not desirable for our DRAM structure or for our D structure. So our structure should be, our desirable should be this leaky structure, maybe this leaky structure, leaky current, or maybe low leakage current. So this is the electrical properties of the sorry, someone trying to join the show. So this is some other property that is some of you may not know. Cumulative probability. Cumulative probability, some of you may not know. That's why I'm just telling. Maybe some of you know very well. Maybe that's why actually cumulative probability means how many devices you are working. That is our most of the cases, whatever we people are doing some devices in a wafer, there are hundreds or more than hundreds devices are there. So if there are a lot of devices are there, so we cannot use these devices. We cannot expect that all the devices work. But our ultimate goal is to our devices, all devices must work. So that's why what we did, we have to measure the several devices. If we think only in a wafer, whatever we have fabricated, maybe 1,000 devices or more than 500 devices in a chip is there, only one device is working. We cannot say this device is publishable. We cannot publish this work. So that's why we have to study the cumulative probability. Means how many percentage of the devices is working. Here you can see the very 100% devices and how much tolerance. This is a 7% tolerance. We are expecting this is 0% tolerance. This is very good tolerance. Tolerance means for one device your capacity is maybe 10 femtofarad, and another device is your capacitor maybe 25 femtofarad. That is not desirable because our one device, two device structure for amorphous, our capacitance should be like that, and for crystalline should be like that. So if you one device is fluctuate like that, or that is not desirable at all. So because we cannot compare them. That's why this is the one of the very important measurement for the memory devices or some other any devices I can say. Again, the leakage current also decreases for the amorphous one as well as crystalline one. So these are the things. Well, now thing is that once we have used some dielectric material, high-K dielectric materials, we already found that several properties are improved. Still, there are people are looking for the improve more. So that's why they are trying with using some other high-K dielectric, that is usually peroxide oxide, AbO3 based oxide, maybe BST, bismuth strontium titanate, STO, strontium titanate. These are the materials. The high dielectric constant is very high, about 300, 100. So you may achieve the very good capacitance. That's why people also tried using this one and also found several good properties and also several good work. So there are a lot of work they have done. Lot of work means this work is going on last maybe 20 years or so. So I don't think this is nothing to or think tell to so many things. Now, one of the important thing is that this is, you can see the effective oxide thickness. Once you use the high dielectric constant, your effective oxide thickness is increases. Whereas if you use the some tantalum pentoxide or ono oxide, silicon based oxide structure, for that your effective oxide thickness is increases. Definitely, if your effective oxide thickness is increases, your design rule also be increases. So for that, your design rule can be go up to 10 nanometer, whereas for the STO structure, you can go up to 50 nanometer technology. Similarly, these things once again here, this is for the RIR structure, ruthenium insulated ruthenium structure. For the electrode, if you change the ruthenium electrode, you can go up to below 50 nanometer technology node, as well as your effective oxide thickness is less, very 5 angstrom order. And wherever if you titanium TIN oxide insulator TIN structure or aluminum hafnium oxide structure, this type of oxide if you use, that time also you can get the little bit definitely higher technology node. You cannot make the smaller devices. So that things both all the things you have to be managed or you have to be make using the different structure as well as different oxide and different things. You have to make like that way. So you have to play with the structure. So don't think that you can make it in a 1 day or 2 day. You have to be play with the several years with the structure and with the things. So these are the DRAM technology, whatever we have discussed few maybe 15 to 20 minutes. So these are the volatile part. Now we will go back to our flash memory. This is non-volatile part. All of you know very well how MOSFET is working. Your flash memory is working fast as one. I can tell one thing. You may know very well there is a, if you consider think as a just FET. This is these three terminals are there: source, drain, and gate. So one is source, drain, and gate. You just consider source and drain in the one line usually. So you just consider a pipe, just simple water pipe. Water pipe, if you in between there is a one valve is there. In a water pipe, just keep in mind how flash memory works. I'm just giving you simple explanation. Think a water pipe in between water pipe, there is a small valve is there. If you open the, definitely water pipe, one end is your input, another end is your output. Water will move. So if you open the valve, that is your gate actually, gate valve you can say. If you open the valve a little bit, your water will flow. So this water flow can be controlled through the gate only. Now for the flash memory, after water flow, there is another after gate, and there is another gate, small gate is there. So this gate, when the gate is open, some automatically electricity leaks up to the first gate, and it will be stay there. It will be automatically stay there after before first gate. So even though you are not opening your first gate, your current, you are getting some current. That's why you are getting this current is already trapped there. This electrons are charged already trapped there. That cannot be moved. It cannot be moved this side and move side in the other side, either or. So this leakage, this water, this can be used as to show you another end. It shows you, yeah, some water is coming, some water is there. You don't know valve is open or not. That's why this is flash memory to work. Means this is looks like a auto always on, even though it is off. So the flash memory usually two types usually say NOR flash and NAND flash. NOR flash is nothing but a random access data. It's like a DRAM, but it's non-volatile. But NOR flash is access data, access policy is very first. However, NAND flash, this is actually NOR flash, and NAND flash is not manufacturing process. This is usually connection process. So how you are connecting with the transistor? I repeat once again, the flash memory also you have to use transistor with the you have to use with the transistor. And in between transistor gate, there we use. Yeah, this is your flash memory structure. This is source, drain. This you can thing the pipe usually actually. So this is a gate portion, and this gate is supposed for all our normal gate structure, normal MOSFET or FET structure. There is nothing is there. Source, drain, and gate, and oxide layer and gate. And here some layer is there, that is ono layer or floating gate layer. Some other layers are there. That's why this is called floating gate memory. Well, So this NAND flash, this actually page access of data, fast programming speed definitely, and slow read speed. That is one of the trade-off of the NAND flash and used for the data storage. The rapid rise of NAND flash that is usually used for the digital still camera, USB, iPod Nano, and everywhere. And NOR flash where you usually use existing NOR market, that is cellular phone and micro drive, etc. They are usually NOR flash are used. So there are a lot of applications are there. So for the application, all of you are using every day, and you know very well. Not using this one. Yeah, this is I think. So these are the structure. These two types of flash memory is there. One is called permanent charge storage in the MOS device. That is called flash memory. So here charge storage is the permanently. So how it is happening? When we are applying some voltage on the gate, control gate, that is called two gates are there. One is called control gate. This is floating gate, and there is oxide gate. This usually we apply the voltage in the control gate, and this electron will move towards the source from to drain. I will tell you a little bit. We have some schematic is there. I will tell you later also. So that time there some electron will be trapped here. That this control gate, what happened? He cannot allow electron to move further in the top direction in the gate direction. So this is usually trapped here. So that's why it's a trapping. Charge trapping is there. So stored charge in the isolated gate. So this is isolated gate, floating gate. This isolated gate in the floating gate here, charge is trapped. Charge is stored. Stored charge in the traps in the dielectric. Stored charge in the nanocrystals. That may be, this is usually maybe nanocrystals, maybe dielectric layer, maybe some other layer, some multi-layer oxide nitrate, oxide structure. These things maybe happen or anything. Some other materials are there, that is ferroelectric materials are there that can be also used, or magnetic materials are also used that can be for the spin based on their spin direction. Okay. So how is it working actually? Yeah, this is the way. So we apply the source voltage, apply the source, maybe source is higher voltage and the drain is a lower voltage. So charge will be going, start flowing. Yeah. So this something what happened? This is if this is higher more the electrons are there, it will try to move towards the drain. But however, this control gate has some biases there. So if there are some bias voltage is there or bias is there, so it will attract some electron. So some electron that can be moved towards the floating gate, and that can be trapped there. That will not move further to the control, because he cannot move this beyond this one, because just like you can rat trap. So electrons are moving or radiators are moving. After moving, he was trapped here, this region, ono region and floating gate region, and he is moved to trapped in this oxide nitride oxide trapping layer. This method is called channel hot electron method, by programming by channel hot electron method. I repeat once again. When we apply this region is higher electron, this is lower electron. If you apply some bias here, some electron definitely move towards the drain. However, some electrons will be wanted to move towards the gate. So once he tries to move towards the gate, he is trapped in this trapping layer, charge trapping layer. So once the charge is trapped here, so this trap, if you remove the bias from the whole system, maybe source, drain, and gate, if you remove the bias, this trapped electron will show you there is some bias is there, some voltage is there. So that's why you can say this is non-volatile, because it stored the data. That's why we can say it's a memory. This is the program part. This can be done by the channel hot electron, and high gate and drain bias is required, and channel turn on. This is a channel actually. You can say this channel is turned on, and this usually problem is that this programming speed is limited. And another problem is that this thickness you cannot decrease further. This thickness you can go up to certain limit, otherwise it will be shorted. So that is the one trade-off. Another trade-off is there, this oxide thickness also. This oxide thickness also you cannot decrease further. You have to be maintain some maybe 9 nanometer or 10 nanometer thickness. That beyond this you cannot move. You cannot go beyond this one. And this erasing bar that is made by the Fowler Noranta electron tunneling. All of you maybe read in your textbook, on a solid state physics textbook. This is one of the tunneling method, and that can be usually used for the electrical erasing process for the flash memory devices. That is high gate bias definitely required, and definitely small current and block erase the open. This structure usually memorizes one transistor and isolation of the and contact in the cell, and this is 10 f square, 10 f square, 10 kh square cell size is there, and this should be the random access. So this is usually the made by the NOR device. This protein gets programmed by the channel or electron for the NOR device. However, for the NAND device, what happens? If we apply the bias here, that is at the bottom, the electron is trapped from the base, your substrate. That is your oxide. Maybe this is silicon oxide. So from here, the electron will be moved to the protein gate and it will be trapped here. So this is made by the Fowler NOR FN electron tunneling. So here, this FN tunneling will dominate for the program as well as erase portions. For that's why it needs a small current. So that is the one of the best thing for the NAND devices. I'm very much sure all of you must be maybe confused about the NAND and NOR and NAND. That is does not matter. That is depend on the how it is happening after taking the electrical properties. You have to be study and you have to get this type of properties. So this is another scaling trade-off of the tunneling oxide. So if you see, this is our thin oxide. Suppose we have used this is thin oxide and this is thick oxide. So thin oxide, electron can move from protein gate to the source, maybe oxide layer channel. It can be easily, right? That is your PF tunneling will happen. However, if the protein gate oxide thickness is very high, that is beyond percolation distance, that is, it cannot move the hair. It cannot directly move to the from here to here. That's why you have to make the oxide layer and should be not less than the 8 nanometer. Okay. So these are the things. So we cannot scale as I told you that we cannot scale vertically. You cannot scale. Sorry, you cannot scale horizontally. You cannot scale vertically also. So you have to make some limit that for that scaling of the flash memory devices. So that's why it cannot scale beyond some 8 nanometer for the tunneling oxide thickness. It's about 8 nanometer from the tunneling oxide thickness. After that, it will be short. So defect in oxide causes tail beats and SILC space limited current kills retention with thinner. So what is retention then? If the oxide thickness is very thin, then what happens? Your device retention means how long you can store the data. Your charge already stored here. So we need to know, our desirable should be this charge should be stored for a long time. Because if we store data in our pen drive, that can be, we want to read it after a year or more than years. So that is how long, that is retention. That should be very high. If this oxide is very small, we cannot get the high retention. So thickness of ONO structure, oxide nitrate oxide structure cannot be scaled. For that, another problem is the protein gate to protein gate coupling is that if you make the several devices to together, means we will not fabricate one device, one wafer, one chip. Also, we have to make several devices. For that, there is a protein gate coupling, because this is one of the actually this line is your actually spacer, is to make the reduce the coupling effect. Coupling effect means one bias of the one device should not be hampered the another device. So that is usually happen or observed from the protein gate devices because of this bigger sizes. So this is another trade-off. So from that, it is already found that it may be about 2000 in the years of 2000 or so, 2005. So it cannot be scaled below the 45 nanometer technology, because these are the issues, because we cannot scale vertically, we cannot scale horizontally. So then this type of flash memory devices cannot below 45 nanometer technology. So that time people are looking for some alternate devices that should be the nanocrystal based protein gate memory devices. So what they did usually, they reduce the size thickness. So there is a 3 gate in between the 2 gates layer or some ONO layer, the multi-layer gates are there. So you reduce this oxide thickness. So they use the some nanocrystal layer, 5 nanometer nanocrystal layer, 1 nanometer nanocrystal layer. Already Sandeep Tiwari already made the devices already, and this device is already in the market, and maybe you will get it. So the silicon nanocrystals or the germanium nanocrystals or metal nanocrystals, usually silicon nanocrystal already the first work, and that nanocrystals can store the data. The electron in the nanocrystals can localize the and localize in the electron nanodot, and the nanocrystal memory device can be used for the up to 22 nanometer technology node. So whatever this previous one, we can go up to 45 nanometer technology node. That can be scaled down below 20 up to 22 nanometer technology node. So there is some advantage of the nanocrystal floating gate memory, the isolated dots along with the Coulomb blockade effect, and that should be the quantum memory effects. Reduce the problem of the charge loss encountered in the conventional flash memories, give rise to the thinner injection oxide, smaller operating voltage, better endurance, and faster write speeds. However, as I told, the silicon nanocrystal is the first report, and after that, germanium nanocrystal also reported by us. And now, after that, people are also looking for the metal nanocrystal, because the metal has some more advantages than the semiconductors one. So this is metal have one of the advantages, a high density of states, a wide range of available work function. That is the one of the important. If the work function is very high, you can store the more electrons, and stronger coupling with the conduction channels, smaller energy perturbation due to the carrier confinement. And that's why nickel nanocrystals I have used, and I have some data or devices like that. We have fabricated this type of devices. This is silicon structure. This is actually SiO2 and hafnium oxide tunneling oxide, and this is actually only SiO2 tunneling oxide is there. And this is another device I will show you later. This is SiO2 and hafnium oxide tunneling oxide there. And this is control oxide. That is usually hafnium oxide, aluminum oxide, tunneling control oxide. Usually, this tunneling oxide thickness is usually very small, about 5 to 6 nanometers, or 2 to 3 nanometers. Also, you can use if you use high K dielectrics. And this oxide thickness is little bit very high. Usually, it's about 15 to 20 nanometers, much more higher than this one. And these are the nickel nanocrystals, about 6 to 7 nanometer, and we have used the nickel gate. So after that, actually we have fabricated devices. We have annealed the devices at the different temperatures, and we can found that several nanocrystals are formed from the TM image, and these are the nanocrystal distribution, how much particle size etc. is there, and from there these are the cross-sectional TM, and this TM we can see the isolated nanocrystals are there. These are the oxide thickness, very small oxide thickness is about 3 nanometers. Sorry, it's about I think 2 to 3 nanometers is there, I think, and nanocrystal size about 3 to 6 nanometers, and this is dioxide layer, control oxide, blocking oxide is there. So we can see the very good uniformity of the nickel nanocrystals are observed. These work we can publish already, and some very old work of definitely, but I have to show because of these things. So these are the nanocrystals layer. These are the single nanocrystals. We can see this about 4 nanometer or 5 nanometer size in the spherical size. So these are the things. So these are the actually main properties of the memory properties. How much memory data is stored. So once you fabricated the devices, yesterday I told that we have to measure the physical characterization. We can found that our device is on the right track. So after that, we can go for the electrical measurement. Then we can find that this device is storing very good. We can see that this 1000 degree centigrade annealed devices, this is a 1000 degree centigrade annealed devices that can be shown very good memory window. Memory window means this is forward sweep and reverse sweep is there. If it's a forward sweep and reverse sweep, this window, this is called the window. This distance between, the voltage between the forward and reverse sweep, that is your window. If your window is too much, big, that is your, you can data store is the mode. So that is you can get up to memory. This is width increases up to 1.66 to 3.7 volt once we have applied the different voltages. So that's why you can say this is silicon dioxide tunneling is better. It's good definitely. But however, after that we have used some asymmetric tunneling layer, that is hafnium oxide layer tunneling layer, as well as asymmetric tunneling layer, that is hafnium oxide, aluminum oxide tunneling layer. From there we can found that the switching memory window is increases more for the once you have used the asymmetric annealing layer. So this is also different devices at different annealing temperature, and we can found that the devices at 1000 centigrade annealed at 5 minutes annealed, that shows the better properties than the others. So this is the CV properties, how much memory window increases with the sweeping voltages, and this is the flat voltage calculation. We have to use flat voltage from the CV curve calculated, and then we have to find the stored charge density, how much charge stored, that using the simple formula, and this N charge equal to capacitor oxide thickness and flat voltage by Q2 ratio. From there we have calculated and found that there is very good charge trap, good amount of charge trap in this one. Another important thing is that we have to find that this device is leaky or how much current it is taking. Definitely this device is not very, I think I cannot say very good right now at this stage. Maybe that time we can say in 10 years back, that time we are saying this is a very good device. Now we can say it's not very good device because its current is very high. So we have to be think to how to decrease the current, as well as another trade-off for this type of device is that even though this is our work, still I can say there's a lot of trade-offs are there. This device is retention is 68% after 10 years after extrapolating. So this is also not desirable. Our desirable should be not be less than 90%. So these are the few trade-offs are there. So that's why that time we have works also asymmetric tunneling there. Barrier. Asymmetric tunneling barrier means we have to use instead of silicon hafnium oxide bilayer structure. So that can be, we can use the favor of the hafnium dielectric materials, and so that we can go beyond the some thickness, beyond the scaling limit we can go. So further, after using the asymmetric tunneling barrier, we can found that these are the some TM lecture, what are the labels. This is hafnium oxide layer, we can found easily, clearly hafnium oxide layer. This is silicon dioxide layer and aluminum layer. So all the things we got it. However, we can mostly focus on the memory window. We can see that this memory window hugely increases. It's about 5.9 volt after using the asymmetric tunneling barrier. So this indicates that if you use the asymmetric tunneling barrier or if you tune the device structure, so you can get a better results. So with that, we have used asymmetric tunneling barrier, and we also found that the memory window is increases rapidly, hugely after at the sweeping voltage increases. So this is the one of the best result we have found, and that is we already published in long time back already. And another thing also for this type of devices, also leakage current also a little bit higher because of our device sizes were a little bit higher. So to decrease that, that's why we more mention their current density. This current density is a little bit higher, but we have to make some devices that should be current density should be in the very lower range, so that we can go for the low power devices. So and definitely retention characteristics are very good for this type of devices, and as well as this is called the endurance characteristics. This means how many times you can work the device. How many times means suppose how many times you are write and erase. The retention is very good, as well as retention is very good, as well as the endurance of these devices. So by this engineering, this type of devices, we can achieve a lot of works already done in the past maybe 10 years back or 15 years back. A lot of work on this field is already done, and these works, I'm not saying this is very good work. A lot of very good works already published in the literature, but now it is almost stopped, this type of work, because of the main problem is that this type of devices cannot go below the 22 nanometer technology. Our desirable, we are looking for the devices that should be the very small devices size. So that's why the emerging devices technology came in the picture. That is that most of the emerging devices technology are the resistive random access memory, phase change memory, phase change random access memory, magnetic random access memory. These three are the, or ferrotic random access memory. These four are the in the race. So once this is these four are in the race, so initial access is very fast, low cost per bit, and this is so definitely this type of devices can go smaller devices. Now I am going back to little bit over our basic things. All of you know very well there are six fundamental relations, that is usually capacitor, resistor, inductor, and capacity. Yeah, uh, charge, voltage, current, flux, and all that are connected with the fundamental relation. Six fundamental relations can be made from this type of devices. So resistor equal to dV equal to RDI, inductor equal to dphi equal to LDI, and capacitor equal to dq equal to CdV, and dq equal to IDT. So 1, 2, 3, 4, 5. These are the five fundamental elements relation you can make. I think something one is missing somewhere. Well, I will tell you later. Yeah, these are the five. Am I right? The five. I am right. So five are very well known. So these are current, voltage, resistance, and inductance. All are the related to each other. So I equal to dq dt, voltage equal to d phi by dt, resistance equal to dv di, and L equal to d psi by di. So all are the connected. We can see all are the connected to each other except Q and psi. A magnetic flux. Q and flux, they are not connected to each other. You may not know. You have not read in your textbook, any textbook yet. So in 1950s, I think, that is Leon Chua, he first proposed that there should be a connection between the Q and phi. That is usually M equal to d phi by dt. That is MM is nothing but a memristor or RM. M is nothing but a memristor or RM. So it is connected by d phi by dq. So this is usually first proposed in 1950s by Leon Chua. Then after that, a lot of works actually done, including Professor K.L. Chopra. A few weeks back, he was expert, former director of IIT Delhi as well as IIT Kharagpur, and he was also fabricated or established macroscience lab where I am graduated actually. So he also observed some this type of IV curves. Maybe you people also observe in your some devices some this type of works. But this type of works usually whatever they got that time, they already published that this type of IV we have got, but they never identified this one. This is a very good work and that can be leads to the future. Right now, these are the hot cake. So this type of work actually what a non-linear in the IV characteristic. But whenever they use the positive voltage or negative voltage, whatever, during forward they found something, and during reverse they have to find the different voltage, different characteristics. It should not be come back in the same path. So that's why this type of works, and this is actually journey of the resistive switching memory, I can say. In 1960s, actually born by it's not everyone found it, but not recognized. I made a mistake. I told you 1950s, it's 1970s. In 1970s, Leon Chua, he actually invented and proposed that there should be a memristor is there, which is connected by the phi and psi, L and psi. So that in end of 1990s, everyone in 1990s, everyone found that when people are looking for observe that phase cannot be go beyond 22 nanometer technology. So that is the one of the scaling issue. That time people are focused on the some other devices that should be go beyond this technology. So that's why people are looking for the hunting for the old data, maybe you can say, and then recognize people identify that this type of device may work. And 1990s, that time which huge work is started, and HP they started working on the working on this field in 2008. Once the company industry people they started working, that time it's recognized as a maybe a good future candidate. In 2013, HP already fabricated the devices and it's now a very hot cake. So this is another history of the RM. So as I told you, in 2012 to 2016, lot of works already done by the several companies. Micronics, Stanford, Sandisk, Toshiba, Panasonic, Micron, Sony, almost all the big companies, they started invested. However, TSMC was silent till 2017. He started working on this field in the 2017. And there are a lot of works till now it's going on, and there are a lot of prospects for this type of industry. So as I told you before, this is the flash memory. Whatever I told you before, I don't want to spend here. Now thing is that why RAM? Problem is that 14-gate memory can be rewritten by passing a large current to circuit. So there is a main one trade-off. There is a usually whatever I showed data, my data. So there usually our current is usually very large. This is one of the trade-off. We cannot go beyond some limit. That is the main trade-off for the, because this device thickness is very high. If device thickness is very high, current should be high. So no one can make it. So this large current physically degrades the cell such that that cell will eventually be not written. Typically, order of the write cycles are usually 10 to the power 5 to 10 to the power 6, limiting flash application to rows where constant writing is not common. Another trade-off of the flash is that the floating gate suffers leakage that slowly releases the charge. So if you have there a leakage current is there, it's just simple knowledge in your house. If your water container has some leakage is there, so it definitely water will be leakage down. So this, if the leakage is there, if charges are trapped, charges are leakage from the this region, trap region, that definitely after some days it will be your charge will be chargeless. So that's why retention one of the major issue for the flash memory devices. As flash scales rapidly downward in size, increase of charge leakage becomes a problem. Due to the prediction of the flash is ultimate device. Theoretically, Memristor can scale to sizes much smaller than flash, because here usually most of the people we are using ions or not we are using here ions or dipoles are usually the main role for the switching property. Theoretically, Memristor can scale size much smaller than the flash, as small as few ions with the weight, because metal ions or filaments are about the fraction of angstroms. So line width on the order of nanometers is possible. RRAM exhibits lower programming currents than the exchange memory or magnetic random access memory. PRAM stands for phase change random access memory, or MRAM stands for the magnetic random access memory, without sacrificing programming purpose and retention. So these are the main advantage. This fast switching speed definitely is because ions are moving here, so definitely it's very fast. Program erase is usually 10 to the power -8 to 10 to the power -7 per second, and low power definitely. Long retention time, as I told few minutes back, that's why it's also a non-volatile. It can scalable because it's a few angstrom with few angstrom or conduction process is happening. That's why you can do scale down. It has multi-level capability, stackable with 2-terminal selective device. That is the one of the important part is that. To device fabricate floating gate is little bit tricky, little bit difficult, and this one, sorry, resistive switching memory is stackable on the 2-terminal selective device. That's why it is very easy to fabricate, and definitely it should be seen as possible. A lot of materials people are using. That is starting from the chalcogenide materials. These are the chalcogenide materials: germanium selenide, germanium sulfide, silver germanium selenide. Silver selenide, silver sulfide, silver germanium selenide, silver germanium sulfide, copper sulfide. Lot of chalcogenide materials are used. Superionic materials, solid state electrolytes, organic materials, CuPC, that is also used. Electric material, BST, BZT, STO, that is also used. Magnetic material, LSMO, MNO, LCMO, complex metal oxide, STO, SGO, PCMO, LCMO, all the things are used. Binary metal oxide, this is the one of the lot of binary oxide we have used, the people are already used. So almost all the materials, almost, I repeat once again, almost all the materials in the periodic table almost used. Those are mostly available very easily. Almost all the materials are used as either reactive material or gate electrodes. So these are the almost playground for the RM developers. This is the periodic table. So resistive switching usually two types. One is called bipolar switching, another one is called unipolar switching. So unipolar and bipolar sometimes happen to be observed in one device, that is called non-polar device. So the AC switching phenomena is usually non-volatile, it must be. It has two resistance states. Keep in mind, I repeat once again, it has two resistance states. One is called low resistance state, another one is a high resistance state. Definitely, if you measure your diode, that is also sometime initially it is low resistance state, and after some time, sorry, initially it is high resistance state. After some time, after applying the voltage, it is low resistance state. So, but the beauty is that for diode, if you apply the voltage from positive to 0 to 5 volt, 0 to 1 volt, it will go in a certain direction, maybe like that also I can say. So however, if you reverse the 0 to 1 to 0 volt, it will come back in the same path. But however, in that case is different. That is the one of the bipolar switching, how it is work. Keep in mind, I'm applying here 0 to 2.2 volt. So once you apply the 0 to 2.2 volt, it will come like that way. This cursor it will move like that way. So after if you apply the 2.2 volt to 0 volt, it will move towards like that way. Not like that way. It will not coming in the same path, it will come back in the different path. But however, if you apply again 0 to 2.2 volt, first initially you have applied 0 to 2.2 volt, then you have applied 2.2 volt to 0 volt, then again you are applying 0 to 2.2 volt, you will not go this path. It will move towards 0 to whatever last path he was there. That means he remembered this path, whatever he was there. So to remember to break this path, to forget to make the or already set the device, I can say, to reset the device, we have to apply the negative bias. So we have to reapply the negative bias. From that, it will come back to first low resistance state, that means high current state, and then he will come back to the 0 to minus 3 volt we have applied, then he come to minus 3 to 0 volt, and he will have to reset there. So after reset, if we apply again 0 to 2.2 volt, then it will move this way. At the first step, whatever he was doing, please follow this animation. Yeah, so it is not coming the same path, it's coming in the different path. So if we apply again the voltage, this is the cursor I am showing here. If we again apply again 0 to 2.2 volt, it is going like that way. So until unless if you are not resetting the device, it will follow the same path. So for that we have to reset the device. So I am applying the until unless you are not resetting the device, it will follow the same path. Means whatever he remember the last path. For that we have to reset the devices. We have to apply again the 0 to minus 3 volt. I'm just showing once again because some of you miss. Yeah. Now I'm applying the 0 to minus 3 volt. So it will 0 to minus 3 volt, then minus 3 to 0 volt. It's coming, reset the device. Device come back to this low resistance state. Sorry, high resistance state. High resistance means low current. It's come back to the high resistance state again. So then again I am applying 0 to 2.2 volt, 2.2 volt, 0 to 2.2 volt, 2.2 to 0 volt, 0 to minus 3 volt, minus 3 to 0. So this is the complete cycle. So that's why this is to set and reset, we have to apply the positive as well as negative bias to polarity of the voltage. That's why this is called bipolar switching. So we are applying the 0 to 2.2 volt, 2.2 volt to 0 volt, 0 to minus 3 volt, minus 3 volt to 0. So that's why this is type of devices we can say bipolar devices. However, for unipolar switching is a little bit different. For unipolar, in one polarity you have to be switched set as well as. So there is a one term was there in the previous slide also. You can see this current is level is there is your almost fixed, not almost, it's fixed, straight line. So because of we have to, when we are applying the voltage, we have to use the compliance current. Compliance current means after certain current we have to clamp the current. That's why we need a very good measurement system as well as the probe station. So this compliance current, we can make the probe station in your ready-made in your home also, not home actually, in your lab also. Some Jugaad technology, by using the Jugaad procedure, because we can make it. That is not a big challenge. Well, so here we can after this level, maybe for this 1 milliampere current is a clamping current. After this current, once the device is achieved to the 1 milliampere current, he will not allow to achieve increase more. So if it is allow the increase more current, so what happens? Your device may be damaged. So that's why this clamping current is there, or that is called compliance current. This compliance current plays a very crucial role for the unipolar devices. So when we set the process, we will follow the same method or the similar method, but definitely not for the same devices. It will happen. It may be happen for the different devices, or maybe same device, depend on the device. So once you apply the 0 to 1.2 volt, it will go like that way. And definitely 2.2 to 0, it will come back in the another path. However, once if you are not resetting the device, that is the device is your reset. Now the device is your set. Until unless you are not resetting the device will move like that way. So to reset the device, we have to remove the compliance current. So if you remove the compliance current, this current will increase. So here it is not, previously it was clamping was there, compliance current was there. Now there are no compliance current. So it will start increasing. So after increasing certain level, due to Joule heating effect, the device current, filament actually ruptured and device current will be fall down to its volt high resistance state. So this is the another animation you can see. 0 to 1.2 volt, we are applying 1.2 to 0. Now again I am applying 0 to 1.2 volt. Now again I am applying 0 to 1.2 volt. Then what happened? It is not going to the previous path. It is going to the whatever last path. So it will follow this path. So now I am applying 0 to less than this voltage, 0.8 volt, the 0.7 volt. Then we remove the compliance current. Then we can see that it's reset. Why I am applying 0.7 volt, not 1.2 volt? If we apply 1.2 volt, that is does not matter. If you apply 1.2 volt, what happens? Your device will reset fast. Then again he will set. So I don't want to set once again. I want to set later. That's why I make that. So that's why here we are one polarity of the voltage is good enough for the switching process. That's why this is called unipolar switching. So this is usually the conduction mechanism. This is MIM structure, nothing but a quite similar structure of the DRAM. This is usually cathode, anode, maybe two electrodes, metal electrodes, maybe platinum, maybe TIN, or maybe AGO, whatever, depend on your device structure. So what happens? There is a one when we apply the voltage, the oxygen vacancies make a conducting path between the cathode and anode. So once they make the conducting path between the cathode and anodes, so the filament is formed. Once the filament is formed, definitely ions are very highly conducting. So that's why your current will be increases. So you are going to the low resistance state. So after applying the reverse bias or maybe a filament rupture by the higher compliance current, what happens? The filament formed in by the ions, that is rupture. So for the binary cases, bipolar devices, the filaments ions are come back to the cathodes, and for the unipolar switching cases, the filaments are ruptured due to the Joule heating. So that's why once it's ruptured, the device is returned back to the high resistance states. That's why your current is low. So this is one of the typical some voltage video, simulation video for the filament formation. Please see. No sound is there. This is the probe. Bottom electrode already from the substrate. The substrate is the silicon, highly doped silicon, hafnium oxide silicon. Hafnium oxide nickel electrode. These are the ions. So once you are applying the voltage, the ions are moving. They are trying to making the conducting path. These are the atoms actually. This is a cross-sectional view. Previously was whatever happening in the inside, that is was showing. Now it is what is happening inside in the cross-sectional view. So this is the filament is formed. Maybe multiple filaments may be formed, but usually nowadays it is established that usually one filament usually forms. Yeah, this is unipolar switching definitely. So here you can see the nickel form. You see, this is current. Once this filament is formed, the current is increases. Once this filament will rupture, it's a Joule heating is there. Red was there. You see here, the red is there. Joule heating is there. After Joule heating, it rupture, and this is down. Current is down. Means high resistance state is gone. That's it. So this is the thing. I repeat once again. So this is unipolar switching for the Joule heating is there. So it is current is increases. The filament is formed. One is current is achieved to the highest level. After that, it is red. So it is heat up by Joule heating, and this is process is over. So these are the things. So how it is connected with the memory structure or devices? So this is usually MOSFET. The MOSFET source, drain, gate, and in the drain side, usually people are used for the MIM bottom electrode. MIM. This is your RAM. So this RAM, once the RAM is switch on, the drain is thinks that this power is always on. So the MOSFET is on, the device is on. So once the RAM is off, that means your drain is seeing that nothing is there. So this is MOSFET is off. So that is the simple observation or simple explanation for the RM structure. These are the several results of the several groups. These are my postdoctoral group. From there, they also published. They are working since lot of 2005, and they are the most of the pioneer group in the RM, and they have done lot of works on the chromium doped SGO, and these are the lot of switching properties. I'm not showing some of the switching properties I'm showing here. This is unipolar switching of the platinum, nickel oxide platinum structure made by the Samsung. This is to a different electrode phase, top electrode phase, how it is affecting. This is interfacial layer, how it is affecting. If you add the interfacial layer, how it will be changed. A lot of work, lot of engineering they have done, and they are still working on. Sometimes it is suppose someone having good AFM setup, they can do some AFM only. Using the AFM, they can only study the switching properties also. So this is by using the nickel probe, a tungsten probe they have measured for the nickel oxide based devices, and they also observe some good switching properties. These are the some work of the titanium oxide based devices, and they deposited on the atomic layer deposition. And from there you can achieve up to 10 nanosecond set time, and the set time up to 5 microsecond. So these are the very good work, I can say. So these are the things I'm not going. Yeah. So another thing that this is a simple properties of the copper oxide. The copper oxide can be used for the RM switching application. So for that, usually there are several conduction mechanism, study of the several conduction mechanism is another beautiful work for the RM. If someone wanted to work theoretically, that can be do. So this region for IV region, this portion is ohmic. This is trap fields limited voltage is there. This is child law, child square law, I proportional to V square. That is also following here. So this is the different draft level in the copper oxide that can be modeled from this characteristics. So these are the things, charge trapping of the copper oxide layer, copper RAM. So they have already studied how much charge is trapped inside the copper oxide RAM. The switching mechanism usually mostly depend on the device structure, I can say, and mostly it can be classified in 4 types. One is called filamentary and conduction path, and Schottky barrier modulation is there, conductivity modulation by charge trapping, and of course defect mechanism. Defect, if your device is some defect, that can be also shows good switching property. Keep in mind one important thing is there. If your device is very good, means your thin film is very good, highly crystalline, very pure, you may not be able to get the good switching property. So further, your device should be very leaky is the best one. Leaky is not that does not mean very leaky means you will not get any. Well, so that should be, you have to compromise, you have to make the several methods, and you have to make several annealing procedure or some deposition procedure, tuning the deposition procedure you have to do it. But you cannot expect that MB grown device can gives you very good switching property, or ALD grown bare device gives you very good switching property. You cannot expect this because this type of things are very good quality. These are some simulation, and from there they found how heat is generated during the switching process. So this is another, I am showing the real time some reported results by some groups, I think Elmini group, Daniel Elmini group, Italy. So they found that how filaments are forming in TM, by TM. This shows. This is made by crossbar, yeah, crossbar. So these are the very difficult measurement procedure. So these are the TM. So once you apply the voltage, you can see these are the ions are making the filament, trying to making the filament. You see, these are the black portions are ions, metal ions maybe, or oxygen ions. I think this is metal ions, because otherwise it cannot be contrast like that way. So this is making the trying to make the filament. You can see. So this is a very exciting work the people have already done. Yeah, this must be metal. Yeah, this is forming the filament. Yeah, almost filament is formed, I can say. Very small blackish color is there. So almost filament is formed. One minute, repeat once again. Yeah. You see, this one trying to making the filament, but yeah, this is also filament is formed here. A small blackish is there, and not only here, also some filament is trying to form already. So this is the one of the real-time measurement. Is very difficult to get, definitely. So already published, made by the University of Michigan. They made it. So there are a lot of measurements, lot of properties they are maybe studied. So I am showing some of my work. This year we have done fabricated some silicon dioxide, titanium, platinum is the bottom electrode, then titanium dioxide. Then we have deposited nickel nanocrystal on it, and then titanium dioxide again. Then we have electrode, platinum electrode once again. Then we have deposited structural properties and found that titanium dioxide is already formed. And we have annealed the devices at different temperature, and from plan view TM also we have found the nickel nanocrystal is already formed, and we can show the some nanocrystals. Then we have found the some switching properties. These are the some IV curve as well as RP curve, and we can found that this is bipolar switching is observed. This device is without nanocrystal. We can say this is the without nanocrystal one, dotted open circle, and with nanocrystal this one. Without nanocrystal one, some poor cycling properties, means endurance properties. However, with nanocrystal one shows very good property than the without one. So these are the devices we have fabricated. These are the also work also I have done. some transparent flexible resistive switching memory. So on the we have used PN substrate. PN substrate, ITO coated zinc oxide is there. Sorry, ITO coated PN substrate, and on it zinc oxide is our electrode switching layer, and AGO is our electrode. And from there, our device is more than 80% is transparent, about 85% to 90% transparent was there. And from there, we can find that the device is very good switching property also. So this paper already, I think this is not under review. This is already published in PL already. So these are the fair comparison of the different work, including our work. So definitely one important aspect of the RM is that we have to make the device should be this ratio should be as high as possible. Ratio between high resistance state to low resistance state should be as high as possible, and definitely current should be as low as possible. So there are a lot of works we have done. Some work shows a ratio about 150, but here we have achieved up to 3x. But our problem here, advantage is that our endurance is more than 450 cycles. This is one of the trade-off of the RAM is that, especially we can say flexible transparent RAM. Flexible transparent RAM is the one of the trade-off is that endurance. That is usually very difficult to achieve good endurance. So that's why we are working on it. And now we are already working on some different one that I will tell you after at the end of this talk. So now I will spend a couple of minutes on the phase change memory technology because we are already running late. So the phase change memory is nothing but a quite similar properties or switching types as the RAM. But thing is that here main idea is that in RAM there only resistance was changing. So they are mostly people are using the different oxides, LCMO, PCMO, etc., and chalcogenides also. But their theme was there, that is resistance of the oxide layer, switching layer was changing when we are applying the voltage. But for the phase change memory, what happened? We are mostly use the chalcogenide material or glass materials. That is usually more than 6 group elements, one or more group 6 elements of the periodic table, usually combined with 4 and 5 group elements. This is group 6 as well as 4 and 5 elements. Then you get this type of combination. These are usually called glass material or chalcogenide materials. So germanium, GST you can say usually short form. So germanium, Sb4, tellurium, germanium, Sb2, tellurium, different composition of course. Then this type of devices, what happen? If you apply the voltage, then what happen? The devices current will change based on their structural change. Here device maybe once you apply the voltage, there is some phenomena is there, structural changes is there. So this structural change give you the amorphous and crystalline structure. I'm showing the structure now. I'm not going to details. So this is usually our device structure. This green one is the heater, you can say. This heater is nothing but a small metal electrode, metal plug. Plug means maybe thick metal. Plug means we make a trench. On the trench, we deposited the metal so that can be used as a plug. This metal plug, once we apply the voltage, that will be heat up. So once you heat up, this is your chalcogenide materials. This is your bottom electrode metal, and definitely you are applying a little bit thicker bottom electrode plug, and this is top electrode platinum again. So once you apply the voltage here between this one and this one, then what happened? This portion heat up. They are either close to this plug, this will be heat up, and there should be initially which was amorphous high resistance state, and then it will be crystalline. That is not permanently crystalline, it is crystalline volatile, temporarily. So once it is crystalline, so your current will be increases definitely. So that will change your current state. So after if you remove the voltage or if you apply the opposite voltage, then what happens? the current opposite current will flow, and this crystallinity will be come back to again amorphous state. So that way your current state again it will come to the high resistance state again. So that's why it is by this way it is this switch, and its cell structure usually one transistor, one resistor, same as the RAM. So here also we need to be faced with the transistor. So I'm showing here again. This is the one of the TM structure. This is your bottom electrode or plug. This is the oxides, insulating oxide. This plug means this is small VI is there, and this is your plug. This is usually heater also. So your GST chalcogenic material is here, and this is top electrode. So once we apply the voltage, your this is portion is heater. You can see stimulation vessel is there, and from there it will be amorphous structure, and it will be crystalline structure. So if you apply the voltage, maybe time with the temperature, your set pulse will be like that way. You have to apply, and reset pulse we have to be applied. Definitely, your set pulse time should be higher than the reset pulse time. So this is the storing mechanism, how it's stored usually. In the amorphous state, there is short range of atomic order is there, and that should be the low refractive index, and that induced your high electrical resistivity. Whereas during the crystalline phase, long range of atomic order and high refractive index and low electric resistivity is there. So this type of devices usually used for the CD and derivative, this type of devices, and refractive index is used for the CD and derivative. Okay, and the electrical resistivity that can be used for the non-volatile memory devices. This is the one of the another schematic I have shown here. So this is the bottom electrode, and this is your resistor, nothing but a metal layer, metal plug, and this is your GST material. Active region is your only this region will be active, and top electrode is here. Okay, so this is your set reset procedure, how it is working, and crystalline at the low resistance state and amorphous in the high resistance state. So these are the writing mechanism. So during set, you have to measure with the time, with the temperature. So you will get the set and reset pulse would be lower than the set pulse. Whatever I told. This is the switching properties of the device. So once we apply the 0 to 1.5 volt apply, then your device will be switch on. This is the switching characteristics type. How is you working? Beauty is that if you have made the devices maybe in space of GST, you have used suppose oxide. So your device maybe looks like method of fabrication quite similar. So that does not mean if you use plug for the RAM, that will not affect too much. So here, but characteristics properties is different. So from these characteristics, you can understand this is the PCM or RAM. So this is the type characteristics. This looks like that way. The set will go like that way. If you reset, it will come back again this way. And if you set again, if you apply the voltage again, it will come back like that way. But for the RAM, if you apply the 0 to 1.5 volt again, it will go back like that way. So that is the one of the difference between the RAM and HCM. So this is the structure, whatever I showed you. I do not need to know this. Well, so this is the PCM phase memory transistor structure. This is one selector and one storage element. Storage element is your nothing but a register or phase change memory. And this is this contain one heater as well as one material of the GST material. And one selector that can be not only you can use transistor, that can be used diode also you can be used for the GST and PCM material. So either transistor or diode it can be used. So at the same here, you have to use the PCM memory in this portion only. This is source portion. So I'm not saying these things. There are a lot of, because I'm running later time, so I'm not want to. Yeah. So now I will tell you a little bit about the MRAM. MRAM is also quite similar structure as the RRAM. So advantage of the MRAM is that it is unlimited cycle. The cycle is very good than the RRAM, and it's fast, right? Fast ions movement, then magnetic movement of the magnetic poles is much faster than the ions movement, electrical ion movement. So that's why this type of device is quite faster than the RAM. But it had some hard problem is that should be external force sources is required, magnetic source, and this type of things are problem for the trade-off of this thing. So another trade-off for this MRAM is the output voltage is the one of the trade-off, and it is definitely non-volatile, but it cannot be go below some application feature size level because of the its magnetic domains are very low. So here is the DRAM, MRAM structure, MRAM switching, MRAM characteristics. So this is the set one. So these are the usually MRAM we use several layer of the multi layers of the magnetic, ferromagnetic and non-magnetic materials. So these are the tantrum top electron, tantrum top electron, and in between there are ferromagnetic, anti-ferromagnetic materials by several layers are there. And these layers, once we apply the voltage between them, then you can find out magnetic ratio. So you can get this type of device structure. Or if you find the voltage, change of voltage, you can find this one. But what is the major things you have to measure here? You have to measure here the hysteresis loop. I'm showing, yeah. I'll tell you later. So this is the, if you apply the magnetic field, you have to find the measure the magnetic ratio, magnetic resonance ratio. So from there you can find that if you get the good hysteresis curve, from there you can say that this device is the good MRAM properties. But how it is connected usually? This is usually our transistor, and this portion is your MRAM. So MRAM is quite this, all the connection is similar to the RRAM also. That's why I mostly focus on the RRAM in the unit. And this is device size is a little bit bigger than the RRAM because this size is magnetic material and several multi layers are involved for this type of devices. So that's why this is one of the trade-off of the magnetic tunneling junction based devices or magnetic RRAM. So there are a lot of methods, a lot of fabrication is going on. Still, it is working on. It's one of the very good work. I think I know, and you all of you maybe know. Some of you maybe know. This is the one of the competitor of the RRAM. Okay. So I'm not going to details for this one. I will spend a couple of minutes for some other works. I'm not okay. Now people are now mostly focused on some computing system, that is neuromorphic computing system. Tomorrow we have a lecture from the Dr. Farman Mangresa from the UK. He will tell mostly much more about this type of applications of the RRAM. A lot of applications is going on based on the Memristors. So whatever present computing system, that is usually von Neumann computing system, that is usually some drawbacks is there. We cannot whatever I am thinking that can be dictated in your computer. Okay. Another thing we want actually, suppose if we replace our human synapse, we have synapse, suppose someone having some brain stroke, Alzheimer's patient, these people have some synapse or some neurons already damaged. So if you replace the neurons, it is usually very difficult to replace or achieve their come back to their neurons. Okay. So this neuron, if we achieve, we can come back or you can replace their neuron with the artificial neuron. That would be very good things. So people are now working on the neuromorphic computing. Yes, neuromorphic computing is nothing but a computing system based on your RRAM and also bionics. People also using for the RRAM for the bionics application. That is also neuron application. So compared to the traditional computational architecture, human brain working is very fast, definitely, and high energy efficiency. So it's only about 21 it will take energy. The energy efficiency of brain is derived from its low power neurons and spike based computation, which is mainly realized by 4 components. That is you already know very well, all of you: synapse, dendrite, axon, and so on. Synapse is the most important component which provides dynamical interconnections between neurons by switching and plasticity. Memristor can mimic the synapse. In Memristor resistance, synaptic weight is changed by applied voltage to the microscopic conductive path called filament. So these are the different applications of the neuromorphic computing. So we can have fast-paced recognition. Already, this is the most of the important thing in your social site. You are in your Facebook. If you apply your parents' picture, upload your parents' picture, so they will automatically recognize who is he or who is she. Your speech also can be recognized, your motion can be tracked, your object can be recognized, and gesture recognition, and most importantly, we can use our replace our human brain, that is bionics. So this is our conventional von Neumann computing architecture. The CPU is there and memory is there in different parts in the computer. Or a whole thing you can say CPU, of course, and there is data connection, data bus is there. But for neuromorphic computing is one problem is that we will make the several data stores, one neuron, one synapse. So this should be several things are there. They can work individually. So if something working we have allotted to him, he will do, or he can do, whoever open. So that is the Neuromorphic architecture, and that can be, suppose in your brain, a lot of several millions of the neurons are there. So they are working randomly, not if one neuron is fixed for this one. Similar architecture here is there. So this is called the neuromorphic computing. I'm not showing these things. Well, so this is your neuron, simple neuron in your human brain. So this is usually one, then pre-neuron and post-neuron. You can come back in your BSc school, HS, 10+2 standard, and you can remember these things, this type of figures you already read. So when your pre-neuron and post-neuron is there, in between there is some fluid is there that is called, or we can say calcium ion or sodium ions are there usually. And when the neurons are sparked, usually sense the information. Suppose I'm speaking with you, and your neuron is listening, and he is sending the message to the another neuron nearby by throwing the pulses or throwing the voltages or energy through these ions. So this structure you can think quite similar, looks like similar to our RM structure. This is your top electrode, this is your bottom electrode, you can think, and there will be oxide layer or switching layer is there. The switching layer is also a combination of the oxygen vacancies or oxygen ions or calcium ions or sodium ions or nickel ions or whatever, depending on your structure. So the quite similar structure is there. So this structure is quite similar. So if we make like that your crossbar structure of the RM, then that can be used for the neuromorphic computing or synapse application. So we have done a lot of works on it. This is the different structures, and this is the oxygen vacancy that can be one quite similar to the calcium ion and sodium ions. And these are the how it's working actually. So when we apply the voltage, that this is voltage is filament is formed, and when you apply the remove the voltage, filament is removed. So mostly bipolar switching can give you the neuromorphic computing. However, one thing I forgot to tell you. So one thing before switching process, one procedure is there that is called forming process. So forming process is nothing but there your device, initial device, that is usually in the high resistance state. Your oxygen vacancies are randomly placed. So to make them aligned in one direction, you need to apply some little bit higher voltage. This process is called the forming process. So that's why forming voltage is always usually higher voltage than the set voltage or reset voltage. So once all the ions are aligned, then again you have reset. That means only this portion is filaments are ruptured. So once this portion filament is ruptured, then again if you apply the set process, then only this portion will be filament will be restored. So that's why you need a little bit less voltage for the set process than the forming process. So this why we can say this is the forming process. This is potentiation. I'm sorry, this color is not there. This is called potentiation for the neuromorphic computing or synapse, RM synapse. This potentiation is nothing but a set process. That's why in a filament is formed, and depression for the neuromorphic synapse for the synapse, that is reset process. We are saying a filament is rupture. So we have measured the several conduction state. So this is potentiation state. This is depression state. So we measure the different pulses. So what our actually goal? If we achieve this potentiation and depression window is very high, then we can say this device is good. And definitely this should be long. So we have to think that how long we can run the devices, or how long we can get the potentiation depression. Means how can Remember, forget, remember, forget, remember, forget. That is usually our truth. So this is our device fabrication. We have fabricated different devices. That is one of the typical devices I'm showing here. Our titanium nitride is a bottom electrode, and we have used hafnium oxide, aluminum oxide. Hafnium oxide is the switching layer. Ti is the oxygen buffer layer, oxygen adsorbent layer or buffer layer, you can say, and Ti is the top electrode, and this is your capping layer. Keep in mind, this is we have deposited by not by ALD, we have deposited by usually RF spot beam. But ALD can do, but you have to anneal the process, but it's not very deep easy. So another important thing, switching for the RF switching, we have to make the device some gradient switching. If you get the abrupt switching process, then it will be not good for the neuromorphic computing procedure. So these are the COSMOS structure we have already fabricated and we already published in the last year in nanotechnology, as well as IEEE transition and electron devices. You can go there and check it. So that is we have devices and we have found the XPS spectra. From there, we can find that these devices having titanium, aluminum, titanium, all the compositions are wells. And these are the abrupt switching we have observed. Abrupt switching means this is, you can see, this is without aluminum doped hafnium oxide. This is hafnium with aluminum doped hafnium oxide. This is abrupt switching we are getting. So this abrupt switching is not desirable for the synaptic property because we have done a lot of experiments. People are already done a lot of experiments. From there, they can found that this abrupt switching will not give you the good synaptic properties. May not be you will get the synaptic property. That's why people are looking for the abrupt switching. So how we can do that? That's why we have done the engineer the device structure. We have doped the aluminum. So that's why we get the aluminum. This is the forming process definitely, but this can be also different from here. So these are the switching process, synaptic properties of the devices, and here how these filaments are formed and how potentiation and depression will be occur. That is already we have discussed. During potentiation, the filament will form, and during depression, filaments will be rupture. But problem is important is that for hafnium oxide based devices, the filament is rupture. Filament structure is little bit thicker filament. However, the filament thickness is controlled by aluminum doping. So if the filament thickness is narrow, you will get the very abrupt, gradual switching. You will get it. So that's why you will get the gradual switching as well as good synaptic property. So this how to improve this linearity. Linearity means another term is there. So if linearity means how we can remember it properly. So that's why you have to make the device should be more linear. Linear means potentiation should be linear, means not very flat. This depression region is not linear. Linearity is very poor. So that's why we are looking for the highly linear, good linearity value. So to get the improve the linearity properties of the Memristor for synaptic application, we have to tune the device thickness and oxygen concentration by annealing, modifying the device structure by adding an interfacial layer, improvement of linearity by modulating pulse width. Linearity can be improved by changing pulse sequence, single and double pulse. That is measurement procedure. Also, when you will measure the devices, that can be also you can get the different way. So the measurement is also another tricky way. We have also published one paper in last year that how we can improve the non-linearity value by tuning the measurement methods. But gradual register switching can lead the good linear switching. So this is the one of the simulation result we have got. So we can see that hafnium devices can give you the poor remembering properties. However, aluminum doped hafnium oxide device can show that the good remembering properties. So we can memorize very well. So that's why you can say that this device is very good. So in conclusion of this 2 days talk, we can say that clean room is very important, and clean room work in the clean room is very important for the device fabrication. And DRAM is still very attractive for its fast switching and inexpensive. Nanocrystal flash is what promising but not scalable. In the race between emerging memories, RAM is still very promising. So I like to acknowledge for my funding, the SCRB, also get some fund, also NIST. I'm also collaborator, National South University, IIT Kharagpur, SN Bose, Jadavpur University, and all of my friends who are working in UK, Europe, Portugal, and all other collaborators, and they are helping me a lot for my work. And I like to request all of you to at this trying period for do some social activity, do something which can help in your society, in your neighbor. If you neighbor something in any way, if you can help, able to help in this time, that is good for our society. Please do that. Thank you all. Thanks for joining this course. Thank you all. If you have any question, please ask. Yeah, you can unmute yourself. You can ask me this.
Hello.
Yes, sir. Yes, sir.
Yes. Hello.
Yes, yes, Dr. Devanjan, please.
Yes, yes. Thank you very much for your nice presentation. It's very nice, and I'm very delighted that you know that a few years back, 5 to 6 years, most probably back, it was typically a nascent stage of the development, and the research was very booming. Right now, it is also booming in this field. But now today, you have discussed this topic so nicely and so easily that one undergrad student can easily understand and realize the thing what is happening. So it's very nice presentation. I have a specific question to you. Sir, can you please explain that how in case of chalcogenides memory like WS2, MOS2 based memory, how the resistance, what is the, I mean, basic mechanism behind it? Because you know that in case of chalcogenides, there is no such oxygen vacancies is there. If I consider the ideal cases, so I mean the few layer or monolayer kind of thing. So as there is no such oxygen vacancies is there, so how the resistance switching is possible? What is the specific mechanism that governed by the the resistive switching? Can you please explain?
Yeah. It's a very good question. So most of the cases, whatever we said here, most of the oxygen vacancies plays a major role for the switching procedure. So if there are a material, if there are no oxygen there, how it can be switching can be happen. So that is a very good question. As I told in one slide, I think there are a lot of methods can be plays role for the switching property. One of the methods are their defects also plays a crucial role for the switching procedure, and metal ions also. So in chalcogenide material, in sulfides materials or copper sulfide, or maybe mostly chalcogenide material, you can say. Yeah, the MOS2 or this type of materials. If you find the switching materials, it may be happen due to the defects or maybe sulfurs. Sulfur plays the main role, or metal ions which are main plays role. So we can say that is maybe CBRAM type we are getting the properties. So depend on the structure, and you have to be depend on the what type of characteristics you are getting. From there you have to understand. So we cannot say from your without knowing the structure, without knowing the IV curve, that cannot. Definitely, their oxygen vacancies are not playing role. Definitely, but I feel it should be maybe dominated by the defects inside the switching layer, or maybe metal ions that can be placed role there.
Okay. So I want to take just 1 minute from you.
Sure. Take your time.
So the thing is that I have a next question. This is can you please describe how, I mean, what is the property that of the material of the structure that define that radon should be in bipolar or unipolar? What is the distinct property?
It's not possible to tell. It's not possible to tell. So there are a lot of materials that can be shown, that already shows bipolar as well as unipolar also.
Exactly. That's why
a lot of materials. That's why that is not a lot of materials that is depend on your measurement procedure also. So we cannot say, or no one, I don't think can anyone say or conclude that this structure you are making, that is you definitely will give you the bipolar, or definitely will give you the unipolar. It's not possible. But still, several already after a lot of literature study, after studying the lot of literature, you can get that maybe titanium dioxide mostly gives you the bipolar properties. Nickel oxide gives you the unipolar properties. That is maybe you have to understand from the literature only. But after you cannot say definitely that will give you. You maybe get the unipolar in that case. We have already reported, we found zinc oxide that also shows bipolar as well as unipolar. Bipolar as well as unipolar. After one cycle of bipolar, it is showing unipolar. That is also a lot of reports are there. So I don't think it can be.
Even after temperature, if you
Sorry.
Increase the temperature after some temperature.
Yes.
For example, the
Yes.
temperature after
Yes,
some temperature.
Yes, you are right. You are right. After increase the temperature, because after when you are doing the measurement, that time your device temperature is increases. That time its properties is changed. So you cannot conclude from here, sir. It's impossible.
Oh. Thank you very much. Thank you.
Thank you, Dr. Debanjan. Nice to see you here.
Yes, thank you.
Any other question? Please ask me.
Hello, good morning, sir.
Yes, good morning, Rupam.
So it was a nice talk.
Thank you, sir.
So I have a specific question on your one of your works.
Please.
You have shown that you have grown a film where HFO2, aluminum oxide, and HFO2, 3 layers are there.
Yes.
For synaptic applications.
Yes.
So my question is, what is the advantages of 3 or 4 or 2 layers beside your 1 layer system?
I got it. I understand. So this is actually not advantage of 3 layer or 2 layer or like that. So what we are trying to do, what I think people are trying to do, they're engineering the structure actually. So okay. Whatever we got in the hafnium oxide single layer of the 5 nanometer, we found that the switching property as well as the synaptic property we are not achieving. So we are just trying trial and error method for the we want to dope the aluminum inside the hafnium oxide simply.
Okay.
Our target was the dope aluminum inside the hafnium oxide. So we found that previously whatever we found that aluminum layer, thin aluminum layer, about 1 nanometer aluminum layer in between hafnium oxide layer shows good switching property in the earlier cases. So that's why we took this method. Maybe that can be crack our purpose. You can try definitely maybe co-sputtering of the hafnium oxide, aluminum oxide. That you can also try. We also tried, but we are not getting good results for this one.
Okay.
Okay. So that's why our target was the insert the aluminum inside the hafnium oxide of layer, because of aluminum can get more oxygen from the hafnium oxide and can meet the defect space. So that is our target actually. Okay.
Okay, sir. So one more question actually. You described that in aluminum doped HFO2 film, your filament will be more sharp and more specific.
Yes. More sharp means more narrow. More
narrow. You showed in I think in schematic diagrams.
Yes.
So is that happening in all kind of dope systems? Like if we dope copper in zinc oxide.
Yes, I got it. Again, the same question like Dr. Acharya asked me a few minutes back. You cannot say for the dope all the materials. You cannot say.
Okay.
Once we get the IV characteristics, that time we are trying, because we are not able to go inside the device.
Yes.
Inside device, we are what is happening, and we don't have the facilities or say real-time measurement system. So that's why we cannot know what is happening. We are speculating, or we are getting supportive data from the IV as well as physical calculation. From there, we are trying to extend the properties. So not all materials. Suppose you are doping with platinum, I don't think you will get it. Okay, so you maybe get it, maybe titanium, you maybe get, but I don't think titanium also is good candidate for this one. Okay, so that's why you have to trial and error definitely. You have to trial and error, and definitely that for trial and error, you have to get the help of the literature.
Okay, thank you, sir.
Any other question? I have already shared the quiz link. Very easy quizzes I have given. So please make it as soon as possible.
Hello, sir.
Yes, ma'am.
Thank you for your nice presentation. I have one query. So could you please go to the slide where you have shown bipolar switching operation?
Well, sure. Actually, I wanted to take the 2 classes for this one. Unable to take them because a lot of speakers are there. Yeah, this one, I think, right?
I cannot see any slide.
Sorry. This one, right?
Yes, yes. So could you please run that what
I
is
understand.
it, animation?
Yes.
So it is
Yeah.
in high resistive state, then it goes to low resistive state.
Yes.
And when you are just stop there.
Yes.
So when you are again coming, when voltage is again 0 volt, so will it come to that -9 current ampere, or will it come up to 10 to the -5 ampere current, because it is already in low resistive state, so it has
No.
not get this
I got it.
state.
I understand you.
Yeah.
So what is actually high resistance state we are saying? If we apply the 0 to some positive voltage, if it is movement in the high resistance state, if it's movement in the high resistance state,
Okay.
that does not mean it will be stay in zero. Definitely 0 voltage means 0 will be there. If there are no voltage, 0 will be there. So if you, what is our reading region, it should be like that way. Can you see my cursor? Our reading region is like that portion. Not here we will read it. We will not operate any device in this region. We will maybe operate here. So if we apply somehow maybe 0.5 volt, 0.5 volt, we will be stay here. 0.3 volt, we will be stay here.
But in 0 volt, your low resistive current is approximately 10 to the -5 ampere.
Yes, actually, this is not 10 to the -9, you cannot say. Actually, this is 0, you can say.
So let's say 0. But when after reaching to low resistive state, that is conducting state, when again you are applying 0 volt, so should it come to the 0?
No, I'm not applying 0 volt, ma'am. I'm applying 0 to 2.2 volt. Just what is the difference? I'm just telling you another example of the for diode. If you have diode, just PN junction diode, if you apply 0 to 0.1 volt, your current will move like that way. This one. Then maybe some breakdown or random integers of the current, you will get it. Then again, if you apply the 2.2 volt to the 0, it will come back to the same path, not this path. You do the experiment in your lab, physics lab or electronics lab, wherever, just go 0 to 2.2 volt and 2.2 volt to 0 volt. It will come in the same path. Here, no, this path will not come. Okay.
Okay.
So here, what happened? You are not reading. You are for reading the voltage. Suppose you are reading pen drive. You have to apply some voltage. Without applying any voltage, you cannot read your pen drive. That's why you are connecting with the pen USB connector. So you have to apply some voltage also here also. In this region, you cannot read. In this region, this 2 dot or whatever, in this region you cannot read. So why I'm saying this is the high resistance state, sorry, low resistance state, because at the same current level, same voltage level, at the same voltage level, maybe 0.4 volt, 0.5 volt, whatever, the previous resistance, previous current was, previously he was in the low current region, about 10 to the power -6 ampere. Now he moved to the 10 to the power -3 region. So that is your low resistance state.
Okay.
Previously at the same voltage, wherever he was. Understood, ma'am?
Okay. Okay. Thank you.